I want you to think about two sets of numbers. Which one is bigger? Your instinct says the natural numbers, obviously. The even numbers are just half of them. Every odd number is missing. So the natural numbers must contain more. But in 1891, a mathematician named Georg Cantor proved that these two sets are exactly the same size. Not approximately, not kind of, identical. And that's not even the strange part, because Cantor also proved that some infinities are genuinely, provably bigger than others. For most of history, infinity was treated like a direction, not a destination. Something you approached, but never reached. Mathematicians used it carefully, like a tool they didn't fully trust. Cantor decided to trust it completely. He asked, if infinity is an actual size, can you compare two infinities and ask which one is larger? To answer that, he needed a way to measure size that didn't rely on counting, because you cannot count to infinity. His solution was surprisingly simple. He called this a one-to-one correspondence, and it works like this. Every natural number pairs with exactly one even number. The rule is just n maps to 2n. No natural number is left without a partner. No even number is left without a partner. By Cantor's definition, these two sets are the same size. This feels wrong. The even numbers are supposed to be a subset of the natural numbers, a smaller piece of the whole. But this is exactly where infinity breaks your intuition. With finite sets, a part is always smaller than the whole. With infinite sets, that rule simply does not hold. Let's see how far this goes. What about the integers? Every positive number, every negative number, and 0. Surely this is bigger than the natural numbers. It extends in both directions forever. But watch what happens when you list the integers in a clever order. You bounce outward from 0, alternating positive and negative. Now pair each one with a natural number. Every integer gets a partner. Nothing is left out. The integers and the natural numbers are the same size. What about fractions? Between 0 and 1, there are infinitely many. 1/2, 1/3, 1/4, 3/7, and on forever. Between any two fractions, there are infinitely more. Surely this is a larger infinity. Here is Cantor's second trick. Arrange every fraction in an infinite grid, where the rows represent numerators and the columns represent denominators. Every fraction ever written lives somewhere in this grid. Now trace a diagonal path through it, snaking from corner to corner, and number each fraction as you go. 1, 2, 3, 4. You have just created a perfect pairing between every fraction and the natural numbers. The fractions, despite filling an infinite two-dimensional grid, are the same size as the counting numbers. At this point, it seems like all infinities must be equal. You keep finding new pairings. Everything matches up. This intuition is completely wrong. Now consider the real numbers. Every decimal number between 0 and 1. Can you list these and pair them with the natural numbers? Cantor proved the answer is no. And the argument he used to prove it is one of the most elegant in all of mathematics. Assume, just for a moment, that you could list every real number between 0 and 1. A complete list, nothing missing. Every decimal is somewhere on it. Now look at the diagonal of this list. Take the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on forever. You now have a sequence of digits taken from the diagonal. Build a new number from these digits, but change every single one. Add 1 to each digit. Now ask, where is this new number on your list? It cannot be the first number, because it differs in the first decimal place. It cannot be the second number, because it differs in the second decimal place. It cannot be the third number. It differs in the third decimal place. It differs from every single row on your list, by construction. But you said the list was complete. You said nothing was missing. This is not a flaw in your particular list. It is a flaw in any list you could ever write. No matter how you arrange the real numbers, the diagonal construction will always produce a number you missed. The real numbers cannot be paired with the natural numbers. They are a strictly larger infinity. So is the paradox solved? Cantor now had two distinct sizes of infinity. He gave them names. Aleph null is the smallest infinity, the countable one. The natural numbers, the integers, and the fractions all share this size. The real numbers are provably rigorously larger, a bigger infinity. Then Cantor asked the natural next question. Is there an infinity somewhere between these two? Larger than Aleph null, but smaller than the real numbers? He believed the answer was no, that nothing exists in that gap. He called this the Continuum Hypothesis, and he spent the rest of his life trying to prove it. He never could. In 1900, David Hilbert published a list of the 23 most important unsolved problems in mathematics. The Continuum Hypothesis was number one. In 1963, Paul Cohen proved something that nobody expected. The Continuum Hypothesis is independent of standard mathematics. It can neither be proved nor disproved within our current mathematical system. It is not true. It is not false. It is simply outside the reach of what mathematics can decide. Cantor's ideas were not welcomed. The leading mathematician of his time, Leopold Kronecker, called him a corrupter of youth. He campaigned to block Cantor's publications and worked to have him removed from his position. Kronecker believed that infinite sets beyond the integers were simply invalid, that Cantor had invented nonsense. Cantor suffered repeated mental breakdowns throughout his life. He spent years in and out of sanatoriums. He died in 1918 in a psychiatric institution, still certain his work was correct. He was right. Today, Cantor's theory of infinite sets is considered one of the greatest achievements in mathematical history. David Hilbert, the same man who listed the Continuum Hypothesis as the most important problem in mathematics, said this. So the next time someone uses the word infinity, remember what Cantor showed us. The natural numbers are infinite. The real numbers are infinite. But they are not the same infinite. Between them sits a question that mathematics has formally declared it cannot answer. We built a paradise. We just don't know how big it is.